Now to prove that if C times U equals 0, then either C equals 0 or U equals 0, where U and Z are vectors and C is a number. We can prove this by considering two cases. Either C does or doesn't equal 0. If it does, then the proof is true. If it doesn't, we have to prove that U equals 0. So all that's left to prove is that if C isn't equal to 0, then U must equal 0. One important property of C, when it isn't equal to 0, is that it has an inverse, which is C to the power of -1. The product of C and its inverse is 1. This is important because it will be used in the proof. So now that C isn't equal to 0, all that's left to prove is that U equals Z. We'll put this part of the proof in the form U equals ... equals Z. Starting off with U, the first line in this proof uses the property of one axiom to expand the term to be 1 times U. We can then expand it again to be the inverse of C times U. Notice that we can do this because we've already shown that the inverse of C does exist, since C isn't equal to 0. We now invoke the associativity of multiplication axiom to swap the brackets. Now we have the term C times U in brackets. And we know that C times U is equal to 0 because it is stated from the beginning. It's a condition that we've stated in the wording of the theorem that we're trying to prove. So in this case, and in cases like these, we say that it is given. We then use theorem 2.4.2, which is that any number times the 0 vector is equal to the 0 vector, which is a theorem that we've proven before, and so this completes the proof. It is worth noting that any one of these types of proofs can be written in reverse. For example, the proof that 2 times U equals U plus U can be started at either 2U or U plus U. This is because the axioms can go in both directions, forwards and in reverse. Now we're going to prove that there is only one 0 in any vector space. That is, that there aren't two or more zeros that are unequal to each other. We're going to do this by starting out with two zeros, Y and Z, and then proving that they are equal to each other. In the first line of this proof, we expand Z to Z plus Y, using the fact that Y is a 0 and the property of 0. We then use the property of 0 again, this time to simplify it, and to eliminate the other 0 called Z. This proves the theorem in only 2 lines. We're going to prove that any vector U has got only one negative. As with the previous proof, we'll start out with two negatives of U and prove that they must be equal to each other. Starting with the negative called N, we add Z to it using the property of 0 so as to expand the expression. We use the property of the negative called M to expand the expression again. We then use the associative property of addition to swap the brackets, which is the only line in which the expression is manipulated. Even though it doesn't seem to do much, it does cause the expression to simplify to something different. We use the property of the negative to simplify the expression. This time we use it for the negative vector called N. And lastly, we use the property of 0 to simplify the expression, leaving the negative m by itself. Thus, we have completed the proof. Here are some more vector space proofs to illustrate the use of the axioms to expand and simplify the expressions. They are a series of implication proofs, supposing that something is true because something else is true. We can still set these out like we did before. Here we're going to prove another very obvious expression in a vector space. Starting with V, that I've coloured in violet, I expand the term using two axioms. I use another axiom to perform a bracket swap, which is very necessary since I have to get the expression u plus v. I can then transform u plus v into u plus w, because it is stated in the theorem we're trying to prove. We say that it's given. I can then bracket swap again, so that I can leave w on its own and make the other term vanish. So then I use two more axioms to simplify the term to w, which, as you can see, completes the proof that v equals w. Here is another similar statement to prove. We'll start with v and manipulate it to become z. Here we're using the first two axioms to expand the expression, then the next one to do a bracket swap, so as to get the term v plus u in brackets. It is given that v plus u equals u, since it is stated in the theorem, so we can use this to simplify the expression. We can simplify the expression again, so as to end up with z. So we have completed the proof that v equals z. Here is yet another proof. We must prove that v equals n. We expand the expression and perform a bracket swap as before. Notice that the zero vector z has been placed on the right side of v instead of on the left like before. We then simplify the expression leaving n, thus completing the proof. Here is a proof that the negative of the vector u equals the vector u. We'll call this double negative of u p. Starting with the vector p, we expand and manipulate it to this expression, so as to get the expression p plus n in brackets. P plus n equals z, since it is given that p is a negative of n, and it is a property of the negative, and this simplifies to u, which completes the proof. This proof contains an inequality. As before, we'll prove that u equals v. We firstly expand the expression out. Since c is non-zero, it has an inverse. We perform a bracket swap using an axiom, and then we can substitute CV for CU, because it is already stated in the theorem, and it is said to be given. We then simplify the expression to be V, so U equals V. This completes the proof. Here we have this inequality statement. It looks a bit difficult to prove, as it is written here, so we're going to try something different. We're going to start off with this statement, which has already been proven before. The contrapositive of this statement should also be true. The contrapositive of it is equal to the statement that we're trying to prove. Therefore, this new theorem that we're trying to prove is true too. So that's the theorem proven, by taking the contrapositive. Here's another awkward theorem. It can't be proven using the normal a equals ... equals b method. namely because U has no reciprocal. It can be proven this way in a field, but we're trying to prove it true in a vector space. So we'll prove its contrapositive instead. In the case of U equals 0, it is already true. But in the case of U not equal to 0, it must be proven that A times U isn't equal to B times U. This is an inequality proof. So starting with A times U, we expand it out to the following expression, which isolates the expression A times 1 from U. We can then apply the inequality by substituting B for A, but it must be noted that this inequality can only work if U isn't 0. This is a sort of radical step, but A and B have been isolated from the expression U so that this step can work. Simplifying the expression again using the following axioms brings us to the expression B times U. Since there was only one not equal to expression in this list of axiom transformations on the expression, this is adequate to prove that A times U isn't equal to B times U, so that completes the proof. Now could you prove these axioms from the rest of the axioms and these first two theorems that we've already proven? Well, it turns out that you can. Starting with 1 times U, we expand it using the properties of 0 and of a negative. Then we use the associativity of addition to swap the brackets. We then use the theorem that minus 1 times U equals N to change the expression. So then we can do another bracket swap, so as to arrive at the following expression, which is 0 times U plus U. We then use the theorem that 0 times U equals 0 to get the expression Z plus U. We then use the property of 0 to get U, which is what we wanted, so that we have completed the proof that 1 times U equals U. Then the next axiom, which is Z equals U plus N, which is the property of a negative, can be proven using the following axioms and theorems. Both theorems need to be used. Here is a proof for the swapping of brackets used in one of the other proofs. Notice that it's not a general swapping of brackets, but only a bracket swap for these particular vectors. Notice where expansion and simplification occur.